Okay, we're actually going to look at two homework problems here. It's 9.2 and 9.6 because it's just one of them. It's the same shape for both of them, but one of them asks for ix and one of them asks for iy. And so we're supposed to determine by direct integration iy and ix of this shape. Okay, so right off the bat, one of the things we need to do is we need to figure out what is k. So we're going to say y at, in this case, we know the value at x equals a, y is equal to a. So y at a is equal to a, and that's equal to k over a, right? So therefore, k is equal to a squared. So we're going to rewrite this equation right from the beginning as y is equal to a squared over x. Okay. Now that we have that, let's actually do the problem. So how do we do this? Well, what do we know? We know iy is integral of x squared dA. Ix is integral of y squared dA. And we know that ixy is integral of xy dA. Well, let's define a little strip. Let's do a differential strip. So let's define this little rectangular strip. Okay, what do we know about that? The thickness is dx, and the height at any point in time is y. So dA is the area of that little differential strip is height times thickness, so y dx. So therefore, when I'm looking for iy, I said iy is integral of x squared dA, so it's integral of x squared times y dx. So it's integral of x squared, and y in this case is a squared over x dx. And in this case, we're integrating from a to 2a, so you end up with a squared integral from a to 2a of x dx, so pretty straightforward. So we're looking at a squared over 2 times x squared, evaluated from a to 2a, and that ends up being 3 halves a to the fourth. So iy is equal to 3 halves a to the fourth. So pretty straightforward, nice and simple. So hopefully that part's the easy part. But now I glossed over something. I did it on purpose, but we'll hit on it right here. We want to do now from 9.6 says now we have to figure out ix. Well, what do we know about ix? Well, ix is simply integral of y squared dA. Okay, so this is a true statement, absolutely true. That's how it's defined. But are we allowed, the question is, are we allowed to say this? Ix is integral of y squared times, back to what dA is right here, of y dx. And the answer is no, we cannot do that. And why can we not do that? Well, why could we do it the one time and not the other time? It comes down to this. Looking at this differential strip, right? So we have this differential strip. At any point along in this differential strip, so when we're looking at this right here, that value x is constant for every point in the differential strip. The dx becomes infinitely small, and whether you're down here or whether you're up here, it's the same x value. However, when we're looking at this portion of it right here, y squared dA, this is clearly not constant. This y here is clearly a different value than that y there. So to go from this step to this step is mathematically incorrect. So we're going to go like this, and we're going to put a big, huge x through there. So what do we do instead? Well, we're not lost. All is not lost. I happen to know what the ix is for a little rectangle. If I had a rectangle of base and height, I happen to know ix is 1/3 bh cubed. Fair enough, right? But what is this little differential strip? This differential strip is a little rectangle. The thickness is dx, the height is y. And I'm going to call this my dix, because this is my ix of the differential strip, is 1/3 base, which is dx, and my height is y cubed. So then if I integrate that, I get ix is integral from a to 2a of 1/3 y cubed dx. So that is integral from a to 2a 1/3. What is y? It's a squared over x, all that cubed, dx. So I'm going to pull all this out. So I'm going to say a to the 6 over 3 integral from a to 2a of 1 over x cubed dx. Okay. Whoa. So when I integrate that, I get a to the 6 over 3 times minus 1/2 times 1 over x squared evaluated from a to 2a. And that gives me a whopping ix excuse me, is 1/8 a to the 4th. So the takeaway, the reason I want to do these problems, so they're really early on problems, but I want to make sure everyone understands this. We're going to draw a differential strip. So I'm going to erase this, kind of make it a little cleaner to look at here, right? We're going to create this little differential strip. In this case, the differential strip is, to me, it makes the most sense to do a little vertical strip. This vertical strip is if when the thickness of dx becomes infinitely small, it functionally just becomes a rectangle. So this one, turns out that doesn't matter, because anywhere in that differential strip, x relative to dA, x is constant relative to dA. So that's all good. But when we're doing Ix, and we're dealing with this right here, again, an absolutely true statement. That is the definition of Ix. But y is definitely not constant throughout the differential strip. So you cannot just go from there to there. So instead, we look at, hey, for a rectangle, we know that the Ix of any rectangle is 1/3 base times height. Well, that's all this is. This is a rectangle. It happens to be really, really, really skinny rectangle, but it's still just a rectangle, right? And so it's 1/3. The base is dx, and the height is y cubed. And then you can just go from there. Now the last part, and this isn't even one of the homework problems for this, but we'll do it a little bit later on, is we're going to say Ixy is integral of xy dA, right? Now obviously, if this y isn't constant, this one isn't constant. So we could have drawn, say, a strip in this direction, a vertical strip, and I didn't make it all the way there. In that case, we could have redefined dA, and we could have done both this equation and this equation without doing the dixy, right? You'd have to redefine dA. I find it easier just to do one strip and go with it. And part of that is because of this right here, that I know that eventually we're going to also want to find the product of inertia. And the product of inertia, you, by definition, always going to have one thing that's there's no way to hold them both constant with respect to dA. So what are we going to do? Well, we're going to go back to this idea of the little rectangle. This little rectangle, what do you know? Well, you're going to say Ixy, parallel axis theorem simply says Ixy bar plus xy times area, right? That's just really straightforward. So what is Ixy bar? Well, we're talking right here, so let's come over here, and I'm going to clean this up again. Clean all that up. And if we look at our differential strip, we have this little strip right here. I'm drawing it a little bit bigger. So where's the centroid of that? Well, it's right in the middle. Okay, so what do we know about a rectangle, the Ixy? That is 0 because of symmetry. Therefore, now I'm going to change this to dixy. So the Ixy of this little differential strip is, the Ixy, which is 0, plus the distance that it moves from this direction here in x and in this direction here from y. Well, what do I know about that? I know that the x bar of this little differential element is how far it is at any point in time from that y-axis. And in this case, it's simply x, right? So if the differential strip is over here, and there it is, and it's the x, and if it's over here, then there it is, and it's still x. And y bar, that little differential element, is always going to be right in the middle. So it's always going to be 1/2 y. So therefore, the x distance away is going to be x bar of the elevation, the element. The y of this is always going to be the y bar of that little element. And now I'm talking about my differential area instead of the area. So I can come in, I can get that information from there, and I can say dixy is x times 1/2 y, and my dA, coming back to here, is y dx. So therefore my differential ixy is 1/2 xy squared dx. So I know what y is. It's a squared over x. So therefore my differential ixy is 1/2 x times a to the 4th over x squared dx, and that cancels with that. So dixy is a to the 4th over 2 times 1 over x dx. And then we can just integrate that. And that's pretty straightforward integration. Integrate both sides, and then so you have your ixy is integral, again, from a to 2a of a to the 4th over 2, 1 over x dx. And then we can solve for that. And you just get ixy is equal to a to the 4th over 2 times natural log of x from a to 2a. So that's a to the 4th over 2. That's a 4, sorry. Log of 2a minus log of a, which, if I'm not mistaken, my math is a little bit fuzzy on this, is a to the 4th over 2 times log of 2a over a. So it's equal a to the 4th over 2 log 2. So that's actually, again, not even asked for in this problem, but the idea is still there. So I want to take just a second to review that we're going to make one differential strip. And this is the way I'd approach all these problems. Make one differential strip. Just commit to it early and go with it. Usually vertical makes life easy. Sometimes if it's given x is equal to some function of y, it's easier to do a horizontal strip. But usually vertical strip's easy. You're going to go through and solve for iy. If it's a vertical strip, iy should be pretty straightforward, just following this equation. If it's a and then you can go through and solve for ix. Well, ix is, again, you cannot use this step right here because it's not constant. So therefore, you're going to say, hey, but I know the differential ix is 1/3 base times height cubed. And so it's 1/3 dxy cubed. Then you solve for ix, and then ixy is never going to be constant. So you're going to define the x bar of the element, the y bar of the element, because again, why is that important? At any point in time, the x bar of the element is how far away. So coming back to here, you have this element here, how far away it is moved from the x-axis or the y-axis, which is a parallel axis theorem. The y bar of the element is how far it moved in this direction, which is also used for the parallel axis theorem, and the a becomes dA because we're looking at the differential element. And then you solve from that. And so it's not that hard. You just got to keep track that you only get to do one of these these 3 equations. Only one of them you're going to use directly. The rest of them you're going to use some modified version of them.